Hello, I'm Álvaro Calafell, and this is the third video about the resolution of the harmonic problems. In the first video, I explained the general procedure for this resolution, and in the second video, I applied this procedure to radial networks. Based on this, the present video shows a resolution of the harmonic problems in three-phased meshed networks. Remember that an electric circuit supplied by non-sinusoidal voltages was solved in the first and second video by applying the Fourier series theorem and the phasor theory, in order to decompose the original problem in a set of DC, fundamental, and harmonic voltages. We approximated the nonlinear load behavior as current sources with constant and known values, which were obtained from the fundamental current and the individual harmonic distortion of the currents consumed by the nonlinear loads. After that, the superposition theorem was applied to solve the problem for the DC, fundamental, and each harmonic by considering the fundamentals of circuit theory. In the present video, we are going to apply this general approach to three-phase meshed networks. The goal here is to determine the distortion of the voltages at the buses of the network. As an example, picture the following three-phase mesh network with the generator and the nonlinear loads connected through the different lines. To solve this circuit, we must study the phase-to-neutral circuits of the three-phase system for the fundamental and each harmonic waveform, considering 0 the DC component of the voltage. For the fundamental circuit, we have the phase-to-neutral circuit of the three-phase system, with the phase-to-neutral supply voltage equal to the line voltage divided by the square root of 3, supplied through the lines. The nonlinear load consumptions, which are represented by means of their fundamental current sources and are characterized by the total power consumption of the nonlinear load divided by 3, which is the single-phase power consumption of the nonlinear load. For all the harmonics, the phase-to-neutral circuit of the three-phase system do not have any supply voltage as it is assumed sinusoidal. We only have the lines and the current sources representing the nonlinear load consumptions. Following the procedures mentioned in the previous chapter, the voltages are approximated to the supply voltages by disregarding the voltage drop in the lines. The fundamental currents are calculated from the single-phase active power of the nonlinear load, equal to the three-phase active power divided by 3, and the bus voltages. With these results, we can solve the harmonic circuit and determine the harmonic currents and voltages at the network buses. The circuit is solved by the voltage node method, with the unknowns being the harmonic voltages. To apply this method, the harmonic admittance matrix of the three-phase system and the current vector with the harmonic currents consumed by the nonlinear loads must be built. The magnitude of these harmonic currents is calculated from the fundamental current consumed by nonlinear loads, determined from the fundamental circuit, and the individual harmonic distortion of the nonlinear loads. We will assume that both currents have the same phase angle, which is equal to 0, putting us in the worst-case scenario which produces the highest harmonic distortion, as seen in the second part of this series. The possibility to randomly fix the phase angle of harmonic currents exists by applying the Monte Carlo method, but this approach is out of the scope of this course. Once the phasors of the harmonic currents are fixed, we can obtain the harmonic voltages by multiplying the current vector and the inverse of the admittance matrix. The harmonic distortion ratios are determined by using the fundamental and the harmonic voltages. In the last 3 videos, we have learned how to solve the harmonic problem in single and three-phase systems by applying the harmonic penetration method in the frequency domain.